Hello, I am Anusha, lecturer in chemistry, GCWA, Guntur. Today, I am going to discuss an important separation technique used in analytical chemistry, that is ion exchange method. The objectives of the topic are to learn the concept, principle, advantages of various ion exchange resins and applications of ion exchange method. The concept of ion exchange method is the separation and purification of ions and charged molecules present in a solution by using ion exchange resins. The ion exchange resins are insoluble organic polymers. The principle involved in ion exchange method is the reversible interchange of one kind of ion with another of like charge between the insoluble solid resin having exchangeable functional groups and electrolytic solution around it. Mode of action. Polystyrene divinyl benzene copolymer. Upon sulfonation, we will get sulfonated polystyrene divinyl benzene copolymer. When a solution containing metal ions is allowed to pass through this resin, the H plus ions of the resin are replaced by the metal ions. In the same way, when the solution containing anions is allowed to pass through anionic resin, the negatively charged ions in the resin are replaced by the anions that are present in the solution around it. It is an old method used for separation process since BC. Aristotle in 300 BC finds that seawater loses part of its salt contents when percolated through certain sand. In 1850, the two agricultural chemists H. Thomson and J. T. Way first reported that certain soils have greater ability to absorb ammonia from fertilizers. By using various clays, they extracted calcium, magnesium, and ammonium ions. They prepared materials of this type by using sodium aluminate and sodium silicate. Later, in 1906, Robert Gans used this type of materials for softening water. In 1927, the first inorganic polymer resin, ZSM5, Zeolite Saponi Mobile, having pore diameter of 5 angstrom, was synthesized by Mobile Oil Company for the removal of magnesium and calcium ions from water. In 1940, the first highly stable organic polymer resin, having greater exchangeable capacity, that is polystyrene divinyl benzene copolymer column, was developed by Galileo to purify radioactive nucleotides required for the atom bomb. This innovation made the complete demineralization of water possible, and this technique becomes industrialized for various applications like demineralization of water, softening of water, separation of charged biomolecules like amino acids, proteins, polypeptides, etc. In pharmaceuticals, for controlled drug delivery and for removal of noxious taste and smell. In fruit juice and beverage industries, for the removal of trace metals, undesirable taste, smell, and color. Ion exchange method. The two main components in ion exchange method are stationary phase and mobile phase. The stationary phase is an ion exchanger and the mobile phase is a solution containing ions or polar molecules. The stationary phase is insoluble in mobile phase and is capable of exchanging ions of mobile phase. The mobile phase should have weak affinity for stationary phase. In nature, we can observe this ion exchange process. Soils have the ability of exchanging cations and anions, thereby hold the nutrients required for plants and act as storehouse of nutrients for plants. The amount of ions that can be exchanged by ion exchanger depends on the number of exchangeable functional groups on the ion exchanger. The total number of ion active groups per unit weight of ion exchanger is called ion exchange capacity. Various soils have different ion exchange capacities with respect to a particular ion. For example, soils with organic matter has cation exchange capacity of 250 to 400 milligram equivalents per 100 grams of the soil. Marmorillonite has ion exchange capacity of 60 to 100 milliequivalents per 100 grams. Illite 20 to 40, smectite 25 to 100, kaolinite 3 to 50 milligram equivalents per 100 grams of the soil. Kaolinite exchange both cations and anions because it has both positively and negatively charged colloidal particles, whereas montmorillonite has only negatively charged colloidal particles. It exchanges only positively charged ions. Highly charged ions, ions with less hydrated volume, highly polarizable ions, ions which react strongly with the ion exchange sites can readily exchange by the ion exchanger. The cations that can be exchanged by acidic soils are sodium, potassium, magnesium, calcium, aluminium, etc. on the negatively charged colloidal size particles of that soil. The anions that can be exchanged by basic soils are phosphate, sulfate, and chloride. By using the same concept in the laboratory, various synthetic organic and inorganic polymers are used for the separation of various ions for different purposes. Types of ion exchanges. Basing on source, there are two types of ion exchanges, natural and synthetic. The examples for natural ion exchanges are claylite, montmorillonite, bentonite, vermiculite, illite, clinoptilolite, sodalite, analcite, smectite, cavolite, geolite, etc. Plant and animal cells, due to the presence of amphoteric proteins having COOH functional group, can act as ion exchangers in alkaline or neutral conditions. Wood, fiber, peat, coal, when oxidized by concentrated nitric acid and concentrated sulfuric acid, thereby the obtained activated carbon act as ion exchanger used in the purification of water, gas, gold purification, metal extraction, demineralization, sewage treatment, air filters in respirators, teeth whitening, production of HCl, to treat poisonings and overdoses in medicine, etc. Synthetic ion exchangers are classified into organic and inorganic resins. The organic resins are different types: polystyrene divinyl based, acrylic based, phenolic based. The example for polystyrene divinyl based organic polymeric resin is Dovex 50. The acrylic based resins example is Amberlite IRA 67. The acrylic based organic polymeric resins are further classified into acrylonitrile type and methyl acrylate type. The example for phenolic based organic polymeric resin is Amberlite XAD76. It is a non-ionic phenol formaldehyde resin. Inorganic resins. The example is artificial geolite ZSM5, the first discovered inorganic resin. Basing on exchangeable functional groups, ion exchanges are classified into cation exchange resins and anion exchange resins. Cation exchange resins are further classified into strongly acidic cation exchange resins and weakly acidic cation exchange resins. In the same way, anion exchange resins are classified into strongly basic anion exchange resins and weakly basic anion exchange resins. The strongly acidic anion exchange resins contain SO3H functional group, whereas weakly acidic cation exchange resins contain COOH, OH, SH functional groups. Strongly basic anion exchange resins contain quaternary ammonium hydroxyl functional group. Weakly basic anion exchange resin contain secondary amine functional groups. The examples for strongly acidic anion exchange resins are Dovex 50. In 1948, the highly cross-linked polystyrene divinyl based Dovex 50 was invented. In 1988, Dow company introduces uniform particle size Dovex monosphere resins. The other examples include Amberlite 200, Amberjet 1200, Dovex Marathon C, Amberjet 1500, Amberlite IR 120, Amberlite 252, amberlite FPC23 and amberlite FPX66. These two are used in food industry. Amberset GT74. It is a special resin with thiol functional group which is used for the selective removal of mercury and cadmium and other heavy metals. Then amberlite IRN170. It is a mixture of strongly acidic cation resin and strongly basic anion exchange resin which is used in household filter cartridges. Then amberlite MB6113. It is also a mixed bed resin which has the capacity of color indication when exhausted. The first invented weakly acidic cation exchange resin was used in 1950 for the recovery of the first antibiotic streptomycin from fermentation broth by Waxman, who got Nobel Prize for his discovery. The other examples for weakly acidic cation exchange resins are amberlite IRC86, which is a gel-type resin used for water dealkalization and demineralization with co-flow regeneration. The other examples are IMAC HP333. In 1946, first strongly basic anion exchange resins were invented. The examples for strongly basic anion exchange resins are Amberjet 4200, Amberjet 4400, Amberlite IRA 402, Amberlite IRA 96 RF. It is a best polystyrene based natural porous resin, Ambersep 900, etc. In 1950, first weakly basic anion exchange resin amberlite IRA 45 was invented and was used in 1951 first time for sugar treatment, and in 1952 it was first used for recovery of uranium from leach liquor. In 1952, chelating polymers were invented. In 1953, acrylic based amberlite IRA 67 was invented by Rome and Haas. In 1957, they introduced liquid anionic exchange materials like amberlite La1, amberlite La2. In 1974, the first commercial boron-specific resin, amberlite IRA 743, was invented. The other examples for weakly basic anion exchange resins are Dovex 3, Ionic HEA31, Rexin 203, Permitted W, etc. Basing on morphology, the ion exchangers are classified into four types: pellicular type, porous type, macroreticular type, and surfaces sulfonated and bonded electrostatically with anion exchangers. Pellicular type. The particle size is 30 to 40 micron with 1 to 2 micron film thickness. The ion exchange capacity is 0.01 to 0.1 milliequivalent per gram of ion exchanger. Porous type. The particle size is of 5 to 10 micron and the ion exchange capacity is 0.5 to 2 milligram equivalent per gram of ion exchanger. Macroreticular type. It is a network shaped resin. It is not highly efficient and has very low exchange capacity. Sulfonated. Low efficient, low exchange. The ion exchange capacity is 0.02 milligram equivalent per gram. Advantages and disadvantages of ion exchange resins. Ion exchange resin can be regenerated due to their exchangeable ability of counter ions. Strongly acidic cation exchange resins containing SO3H function group are regenerated by HCl and NaCl, but high concentrations are needed. These can be used at all pH levels. Weakly acidic cation exchange resins containing COOH functional group can be regenerated easily by using HCl. These can be used at pH 5 to 14. At low pH, the COOH cannot dissociate. Therefore, it cannot replace cations of NaCl, Na2SO4 as strongly acidic HCl and H2SO4 byproducts are formed. The reaction reverse snap. It can also not replace cations of weak base like ammonium hydroxide as the resin becomes strong electrolyte which dissociate completely. Thereby, the resin cannot displace ammonium ions of ammonium hydroxide. Strongly basic anion exchange resins containing quaternary ammonium hydroxide functional group which are prepared by chloromethylation of polystyrene followed by reaction with trimethylamine or with dimethylethanol are in their chloroform are first regenerated to their OH form before using them in demineralization process. These resins can be regenerated by using NaOH and NaCl, but high concentrations are needed. These resins can be used at pH range 0 to 12. At higher pH more than 12, the resin cannot dissociate and exchange is not efficient. Weakly basic anion exchange resins containing secondary amine groups can be regenerated by using sodium hydroxide and calcium hydroxide. These can be used at pH range 0 to 9. These resins cannot exchange ions of NaCl, Na2SO4 as strong base byproducts are formed which restrict the dissociation of ion exchanger by reversing the reaction. The strongly acidic anion exchange resins are used in their sodium form in water softening. In their hydrogen form, they are used in demineralization of water. The typical ion exchange capacity is 1.9 to 2.2 mg equivalents per liter. The weakly acidic cation exchange resins in their hydrogen form are used to remove divalent ions like calcium and magnesium from alkaline solutions. The typical ion exchange capacity is 3.7 to 4.8 mg equivalents per liter. The strongly basic anion exchange resins in their hydrogen form are used to remove all anions. In their chloride form, they are used to remove nitrate, sulfate and other several ions. The typical ion exchange capacity is 1.0 to 1.5 mg equivalents per liter. The weakly basic anion exchange resins are used after cation exchange for the removal of chloride, sulfate, nitrate and other ions of strong acids. But they cannot remove weak acids like carbonic acid and silicic acid. The typical ion exchange capacity is 1.1 to 1.7 mg equivalents per liter. In separation process, by using ion exchange method, thin layers to columns are used. Applications of ion exchange method. Ion exchange method is used for separation purification process. Let us see the demineralization of water. When raw water is allowed to pass through cation exchanger containing cation exchange resin having exchangeable H plus ions, the H plus ions of the resin are exchanged by cations present in water. The resultant water is then allowed to pass through anion exchanger containing anion exchange resin having OH minus ions. These OH minus ions of the resin are replaced by the anions that are present in water. Thereby, the resultant water contain only hydrogen ions and hydroxyl ions and make the water pure. Let us see the softening of water. In water softening, the cation exchanger contains cation exchange resin having Na plus ions. These Na plus ions are replaced by cations that make water hard, such as Mg2 plus and Ca2 plus ions. In water softening, zeolites can also be used as they contain the chemical composition of Na2O, Al2O3, XSiO2, YH2O, which are hydrated sodium aluminosilicate. Due to the presence of Na plus ions, the Na plus ions are replaced by the hardness causing calcium and magnesium ions in water, thereby make the water soft. The exhaust resins can be regenerated. By regenerating the exhausted resins, they can be used further. Let us see the application of ion exchange method in separation of amino acids. Urad dal contain 9 essential amino acids such as threonine, methionine, tryptophan, valine, leucine, isoleucine, histidine, lysine, arginine. The pH at which the amino acids attain both positive and negative charges on respective amine and carboxyl functional groups is called isoelectric point and the ion is called Twitter ion. At the pH below isoelectric point, the amino acids are in their positively charged form with NH3 plus and COOH groups. And at the pH above isoelectric point, the amino acids are in their negatively charged form with NH2 and COO minus groups. When the solution containing mixture of amino acids is passed through cation exchange resin by using buffer solution of pH 5.7, the amino acid with isoelectric bond less than 5.7 is in its negative form. Here, that is 309, isoelectric bond 5.6 and is not exchanged by the cation exchange resin and eluted out of the resin first. The other amino acids with isoelectric bond more than 5.7 are in their positive ion form. When the variation of isoelectric bond from the buffer pH is more, that is, when isoelectric bond is more for any amino acid, that will be more positively charged and exchanged strongly by the H plus ions of the ion exchange resin. Here, that is arginine, isoelectric bond 10.76. Thereby, by changing the pH of the buffer, the various amino acids can be eluted separately from the resin. Let us see the application of ion exchange method in lanthanide separation. When a solution of lanthanide ions is allowed to pass through cation exchange resin, the small size hydrated lanthanum 3 plus ions exchanged firmly by the H plus ions of the resin, whereas the large size hydrated lutetium 3 plus ions bonded less firmly to the resin. By using citrate buffer of citric acid and ammonium citrate, the ammonium ions replace the lanthanum 3 plus ions and the citrate ions form stable complexes with small size lutetium 3 plus ions and thereby the lutetium 3 plus ions get eluted fast from the column. The other applications of ion exchange method include in catalysis, in sugar purification, in food industry, in pharmaceuticals, in gold purification, for removing unwanted color pigments, bitter taste causing ions, poisoning ions, etc. Thank you.